Okay, so hello everyone. Welcome to this presentation for the talk named Reliable in-memory computing with unreliable devices and circuits, led by Professor Yu Kevin Kao from the Arizona State University. So do you hear me? Is everything well on the live? You can use the chat. There's no problem with that. And don't forget to type your name and affiliation if you want. Oh. Tac. So this talk is sponsored by Circuit and System Society through the Distinguished Lecturer Program. Up. Okay, so everything is okay on the live. And up. So first, I will give a little bit of presentation on what is IEEE, what is CAS, and who are we. Then I will present Professor Yu Kevin Kao, and there will be the presentation, the talk. So, what is IEEE? This is the world's largest technical professional organization. It counts over 427,000 members in more than 190 countries. So divided, the world is divided in 10 regions, counting 344 sections. So IEEE is an organism that publishes more than 200 transactions, journals, and magazines, as you can see here, as TCAS, IEEE Access. It has 39 technical societies, such as that are groups that focus on specific area of research, such as circuit and system, like today, but also solid-state secret society, or more specific, like electronics in medicine devices. There is also affinity groups, like Women in Engineering, that are groups that focus on less technical subjects, like non-professional things. And IEEE sponsors also more than 2,000 conferences and events in more than 106 countries. So today's event is sponsored by CAS Society through the Distinguished Lecturer Program. So CAS Society is focused on the theory, the analysis, the design, the tools, and the implementations of circuits and systems. In 2023, they sponsor 16 conferences all around the world, like ISCAS in USA or ICAS in Asia. And the Distinguished Lecturer Program is a program that allows CAS members to invite a lecturer to talk, to present a subject as today. So CAS Society counts 19 distinguished lecturers in its roster for 2023. For people that don't know the branch, we are the Lille IEEE student branch, the student branch associated to IEEE in France, in Lille. So we are a group of PhD students working together to organize conferences, workshops, and meetings dedicated on topics and fields around the thematics of IEEE. Actually, currently we count 2 technical chapters, SSC donc and CAS, 1 club and 1 affinity group. We also propose podcasts in which we interview the lecturers that we invite on their experience as PhD students, but also on their career. There are currently 5 episodes, and they are available on Spotify, but also on our website, where you can flash the QR code and visit it, or the link is written IEEE Lille.fr. We are also present on LinkedIn with the same name, Lille IEEE student branch, or with this QR code. So, and today we have the pleasure to receive Professor Yu Kevin Kao. He did his master's degree in biophysics in 1999 in the University of California in Berkeley. Then he pursued by a PhD in electrical engineering that he obtained in 2002 in the same university. Now he's professor in electrical engineering with the Arizona State University. And its research interests include neural-inspired computing, hardware design for on-chip learning, and reliable integration of nanoelectronics. He was also associate editor of IEEE journals, and he took part on the technical program committee of many conferences. So thank you, Professor, for being there today. And now the floor is yours. So I think
yes.
Okay.
Yeah, thank you very much, Matthew. And it's my great pleasure to meet everybody online right now. And I hope I can visit you in person in the future. And today, the topic of my talk will be on the reliable in-memory computing to handle unreliable devices and circuit issues over there. So please feel free to stop in the middle to ask me questions. And for in-memory computing, one of the motivations to develop is to drive the AI applications of that on hardware with high energy efficiency. And AI is everywhere today, especially with recent ChatGPT and other new algorithms coming out. For example, here, I use ChatGPT to generate some fortune cookie, and some are interesting, and some are just like confusing, right? Like the future is in your mind. That's kind of confusing. And AI can also generate those paintings, such as the left side, using the same tool by the Open AI company. I ask questions to draw a picture of fortune cookie plus AI. Give me a white paper, don't know what's going on. Those are just interesting things. But what really impressed me from fortune cookie is the bottom one, which is a real one, not invented by AI. This one, I received this one in my pocket about 15 years ago after having a lunch in a Chinese restaurant. When I open it, it says digital circuits are made from analog parts. And I was really impressed because, from fortune cookie, it usually tells you your future. And this is really technical and fundamental of that. So for me, as a digital designer, I keep this one in my pocket, and I usually show people around this one because this one is actually true. No matter whether you are doing digital design or high-level system architecture stuff, but keep in mind that the bottom of the technology is an analog device over there. And this one also will be related to the topic I'm going to talk today. So in this sense, the background why we care about this one, because everything goes up. I'm not talking about gas price or the food price and other ones. I'm talking about the digital data and also the algorithms of that. Nowadays we have more and more sensors from the XR, AR, VR, XR, and those headsets, and also for the phones. For iPhone, the front camera, the size has increased from a couple of megapixels to more than 40 megapixels today. What does that mean is that nowadays all those sensors can collect more and more digital data for us to process. On the right side, I present the scanning map of all those algorithms from computer vision to transformer and other types of that. The blue one is for computer vision, and the red one is even faster, is for the GPT and other types of transformers. The bottom gray one is for the classical Morse law, 2x per 2 years. But you can see that those algorithms, their scale goes up much, much faster than the Morse law. If we put the left side and right side together, that means we now, for the hardware, for the processor, it has to handle much larger volume of data to process. And in addition, the processing algorithms, like those AI algorithms, are also much, much more complicated and larger than before. Both will add a higher pressure and a higher demand on our processor. For our processor, it typically follows the so-called von Neumann architecture. You have a separate two units, one called memory and one called the computing part of that. In the computing, it has a control, the ALU, the cache, and all those parts together, right? The data will transfer from the memory into your computing chip, and then go through the cache as a buffer, and go through the computing of the ALU to process of that. Even before AI happens, if you look at right side, a figure analysis done by Professor Horowitz from Stanford University, it already stressed a lot on the memory and also data movement on the chip of that. So those are the parts. If you see that one, keep in mind that the x-axis here, which is energy, is in a log scale, so which means your memory and also the energy consumed by read and write the memory of the DRAM off-chip access. For SRAM, which is a cache for on-chip, there are several orders of magnitude higher than the compute energy you need on-chip. So indeed, in the volume architecture, the memory movement and data movement across different components here is a key to limit the performance of your design. And if you consider that one in the background, the future does not look quite promising. And this is a trend for processor. We have seen the scaling role of that. And for the processor, people do their best job to improve not only the Moore's law of the device, but also the architecture of the processor. So the entire performance scaling of the processor goes better than the Moore's law of 2x per 2 years. It actually goes about 3x per 2 years. The real problem is the bottom one, these two green and blue links here. They are for the link between the memory and the processor in the volume architecture of that. The green one represents the link between the DRAM, like the DDR and HBM, with the computing processor. And the blue one is for the high-speed I/Os to connect different chips, such as the PCIe and other types of that. And by the way, this one already includes the recent 3D technology of the HBM that have multiple stacks vertically connect the logic and the multiple layers of the memory chip altogether. But even that, because of the analog nature of those high-speed I/Os, and also because they have to travel a longer distance to deliver the signal, their scaling really lags behind everything else. It only goes about 1.4x per 2 years. As this trend goes on, the gap between the memory and computing will go larger and larger. That's a real problem for the von Neumann architecture, a so-called the von Neumann bottleneck of memory access itself. How do we solve that? Well, let's look back of the evolution of the processor design. So if the memory, number one reason is for move data from DRAM into the chip, how do we hide that? Well, the first idea is to increase the buffer of data storage on the same chip, or the cache size goes larger and larger. So a common technique people are using in the acceleration of AI and other algorithms is to have something called a ping pong strategy. They basically double the size of a cache. So when one side of the cache is receiving data from the DRAM, the other side feed the data into the computing. And by doing such a pipeline, it hides the latency of memory access versus computing you need if you do it right. And you can see that from the right side, by doing that one from the CPU by Intel and then to the Google TPU and to the amazing size of the Tesla, the autonomous driving chip of that, the size keeps going up and up, more than 64 megabyte today, or even some recent chip is over 100 megabyte for on-chip cache of that. By doing such an architecture innovation, it can drive the energy efficiency to above 1 TOPS per watt. But that's not enough, and people are still trying to have more ideas of that. If the data movement is a key issue, then if you look at the AI computing actually involves lots of dense linear algebra operations, especially the multiply and accumulate in the operation. And which means lots of these computings can be done in parallel. And to support that, people further develop an array structure of the processing and the memory to bring the memory one step closer to the processing element inside. So this is like a more like a systolic array and other structures ideas people have to break the entire computing and local buffer into multiple components of that. Each one has its own computing engine and its own local memory. And they can have an array of them to process the mathematics in parallel. And this is also the architecture behind the GPU typically inside. And by doing that, as people demonstrated, we are able to push the computing power from a single digit of TOPS per watt to tens of TOPS per watt. So now the memory is even getting closer to the PE. And that drives the final idea of this called in-memory computing. Basically, we say that instead of moving the data and separate the memory and data together, can we put the computing inside the memory array itself? So now the computing and the memory are fully integrated together. And this is really appropriate for the MAC operation or the multiply accumulate of the AI computing, because more than 70 or even up to 90% of AI computing is about MAC operation in the linear algebra of that. So now the key idea is that if you look at regular one to the left side, that's how people do the AI computing, do the typical digital computing, right? You pre-store some weights from the AI model inside the memory array, and then when you need it, you sequentially read them out. And outside of the memory array, you have a computing engine called the PE. And then you mix the data and the weights together to finish the linear algebra of the MAC operation and generate the output. In this case, the read of the memory is sequential. The computing can be parallel, but also depends on how many data you can read out from the memory of that. On the right side, that's a principle of the in-memory computing. They switch the data of the word line control of the memory into an input. And then when you open it, they open the entire one, not only just one row of the memory, but they open the entire one. Then for the read process, the input and weight are actually do the local multiply inside of one memory cell. I'm going to discuss more details afterwards. And then when you look at the vertical ones, because you have multiple rows open together, then the readout will become a cumulative result of multiple rows together along the same bit line. So in this case, the multiply is done at the bit level, and then the accumulate is done vertically through the bit line. So then within one shot of parallel computing, you can finish a MAC in one shot from the entire array of that. And within this principle, we are able to achieve more than 100 TOPS per watt. That is two orders of magnitude better than the advanced digital computing today of that. So this is why people want to innovate the in-memory computing of that. So that's why in recent years, we have seen many test chips to demonstrate and implement such an in-memory computing idea on silicon. And this ranges from the classical digital ones using silicon to do that, or using the advanced non-volatile memory of that one. There are many flavors of that. In today's talk, I'm not going to go through every piece of the silicon chip, but I'm going to focus on two sort of design examples to demonstrate the challenges and success of in-memory computing. One is more traditional, using the silicon or the SRAM based, and the other one is using non-volatile memory based one. And here, this table actually summarizes lots of different flavors of in-memory computing. For the SRAM, it's really precise, but the drawback is that every SRAM cell is big. It has to at least 6 to 8 transistors to finish that function of that. The write is fast, but also you have to deal with the leakage issues inside of that. People also demonstrated the embedded DRAM of that. It's also 1 bit, but the memory cell size is smaller than SRAM. It is also fast. However, for DRAM, every time when you read it, it's destructive. You have to write it back. That causes additional overhead and energy consumption of that. And one of the also another popular choice people do is a flash or the floating gate over here to store multiple bits of data inside of one device of that in a small footprint of that. But flash itself still has some issues of CMOS compatibility because it has to be driven under high voltage, and the write process is also slow. The final choice of that is a non-volatile memory, such as RRAM based, phase change memory based, MTJ, or other types of ferroelectric materials of that. These ones, if you do it right, it can also store multi-bit into one cell, and that improves the area efficiency as compared to SRAM. The write process is typically slow, and in addition, we have to deal with all kinds of variations inside. Indeed, for all types of those different in-memory computing designs, there are 3 main challenges. One is robustness, and how can we make sure such an in-memory computing at such a large scale can be as robust as possible. Second one is the peripheral circuits, and how do you read the data out? How do you manage the entire computing and then convert data output into a regular digital environment of that? And finally will be scalability. Can we make this in-memory computing tile as large as possible? Those are things, some are fundamental, some are practical issues of engineering solutions over here. So I'm going to present those, some understandings we have done so far to tackle those issues here for both SRAM and RRAM. Let's first start from the SRAM side of it. I'm going to show you some examples. People have done that one. For SRAM, the observation is that the control signal of the word line to access each bit cell is actually can be considered as a 1-bit multiply, because only when both the word line signals and the weight inside it are 1, you get the readout as 1. So that's mathematically a single bit multiply between the word line and the pre-stored value inside the SRAM. So based on that, we can do the multiply inside it, and then we need to see how can we accumulate the result vertically through multiple rows of the SRAM together of that. But before that, we also need to be careful. When we say multiple rows read out from that's already really challenging, because for SRAM, each single bit is really tiny. A reliable read for a regular SRAM is already challenging because of process variations and the scaling issues involved, and also leakage and other parts, right? And now we're talking about open all the rows together. That dramatically increase the difficulty to manage a reliable computing and also a reliable read process to add more complexity to a timing diagram when you operate the SRAM. And for the analog operation over here, it's intrinsically much harder. This is a fundamental problem here. So this is, compared with digital, analog is much more sensitive to noise, and also it's also much more sensitive to nonlinear operations of the device and the variations from everywhere, from the device, from the interconnect, and from the circuit themselves. So this is really fundamental. People have to be really careful to design the SRAM in the in-memory computing environment. I will give 2 examples here people have demonstrated so far. And one is called XOR SRAM. In this case, they have several transistors in addition to the 6T inside the SRAM itself. And then this essential one is a 1-bit XOR function, or the multiply function of that. The trick when you do the accumulate is that when they open it, they actually when you open a transistor here, right, it becomes a resistor over here. And then if you have vertically multiple bit lines, depending on how many of those transistors are connected to the VDD, how many of them are connected to the ground, you serve as a resistive divider across the vertical line of that. And that's how they do the accumulate function of that. So they actually open multiple rows together, and depending on the resistive divider between all the rows as a sum result to decide the final output is 0 or 1. This is a single bit. And for this kind of design, if you want to achieve multi-bit precision of that, you have to linearly increase the number of the arrays to match the number of precision you want in your algorithm itself. And this one is successful. For 1 bit, they can achieve more than 400 TOPS per watt. But if you really look at the design, there are a couple of issues involved. For this one, the linear operation region is really narrow as one side issues here. It's within several tens of millivolts, which is actually hard to do a large-scale design to control such a clean environment of that. In addition, if you look at the power consumption, the driver, not the SRAM bit, is a majority part of the power contributor here. So all those ADCs and other peripheral circuits, they add together will be more than 90% of the energy consumption of that. So these things is a limitation of that. And in addition, when you do the resistive divider of that, and during the read process, you actually have a short circuit between the VDD and the ground. That also pushes up the leakage power and other short circuit power concerns here in this design. By recognizing that, an improved design, which instead of using the resistance but using the capacitance as a divider, was proposed. This is called C3 SRAM and published in the JSSC 2020. In this case, instead of using the resistor in the memory array to serve as an accumulate function over here, they use the additional capacitor here to serve that one. So in this case, when you open each one here, when the output from each one is 0 or 1, and then look at the vertical one, there will be multiple capacitors to link that one out. And that also serves as a capacitor divider to decide whether the accumulated result along the vertical line will be 1 or 0. So by doing that, this one is more efficient of the energy, because now the short circuit power through the resistance are gone of that, right? So this one can achieve more than 600 TOPS per watt it is still single bit for all those SRAM based ones, because SRAM, the memory cell is only 1 bit, so you can only do the 1 bit operation of that. And for capacitor, it is also sensitive to all kinds of variations. Now it's not only device variations, but depending on how you implement the capacitor, it can also be sensitive to temperature and other effects, and also how many bit lines and how the metal capacitance and the parasitics will contribute into it one out. So in this case, still it is really highly sensitive to that. And also it's not really scalable, because once you increase the size, the amount of variation will also go up, and that will limit how big each one will be. Good news is that for the power ones, the capacitive part now becomes the dominant power, like more than 30% is because of the capacitance and operation of that. The periphery is now reduced from 90% to about 40%. So that's good news of that. But still ADC is more than 20%. So overall speaking, that those periphery circuits, including ADC and the decoder and other parts, takes about more than 50% of the total power consumption into it. And that's, again, we can see that those robustness, the periphery circuits, and scalability, those are the key issues in the SRAM-based in-memory computing. And this, as a quick summary, this is a table people we connected from recent years for the in-memory computing, the CMOS-based solutions over here. The blue dot are the test chips for the SRAM-based in-memory computing, and the black dot are the traditional digital Mac. And if you look at the left side, indeed, the in-memory computing achieves 10 to 100x of the energy efficiency, and push the energy efficiency from 1 TOPS per watt into 100 or even 1,000 TOPS per watt. And that really helps the AI computing. On the right side, if we change the y-axis from the throughput into the memory size, and majority part of the in-memory computing are at a much smaller scale versus the digital Mac. So because of the operation inside, it's really hard to design a large scale of the in-memory computing. So you have to have lots of small tiles and using on-chip network to connect them all together. Any questions before we move to the next topic? Please feel free to ask me. If not, I'm going to move to the second part of my talk. So we just review the SRAM-based in-memory computing. And now let's see the other side, or using the non-volatile memory. In particular, the resistive memory called RRAM or RRAM or memory resistor to solve that. For this one, we're going to still emphasize that you're going to see the similar challenges, but maybe from different issues coming out, like the robustness. In the SRAM-based, it's more on the circuit part of that, and also CMOS themselves, and also interconnect. For the non-volatile memory, it's mainly from the non-volatile memory device itself. And then we are going to also, again, to see the peripheral circuits because of the ADC conversion and also scalability issues involved together. So if you look at that one, this is a principle how we construct the non-volatile memory ones for the in-memory computing. Left side showing the one layer of the neural network inside the AI algorithm. Right side showing the so-called the crossbar structure of the in-memory computing using non-volatile memory. Each cell or each cross point has one memory cell, like the RRAM, plus a single transistor. This is called a 1T, 1R structure as a selector to decide which point you're going to access of that. This is mainly used for the programming purpose or the write procedure. When you do the read, you open the entire one together, and then the current and the voltage relationship matches the mathematical relation of the neural network as a weighted sum of the input altogether of that. And that's really a beautiful map to drive the analog computing, because now you can reliably open the entire array together. And in addition, one advantage of the non-volatile memory versus SRAM is that now at each point, depending on which type of device you choose, you can code multi-level of the value inside, and that improves the area efficiency when you do the analog computing inside it. On the other side, if you look at the real device property of that, this is not as clean as SRAM. Right? SRAM is 1 bit, and this is a relatively precise 1 bit of that. But for the RRAM itself, or the RRAM itself, this is the measurement data from the 65 nanometer RRAM of it for the depression part and the potentiation part of that. You can see that data does not really follow a symmetrical linear line. It actually has a nonlinear. It has large amount of variations in both processes we have seen here. So that will degrade the accuracy when we map it, because mathematically you prefer this one is as precise as possible to match the mathematical value of that, but the device or the physics of that one does not really follow that. And so the accuracy loss is the #1 problem in the RRAM-based in-memory computing. And this is a simple example. Depending on how much variations you're going to experience, you're going to see that the accuracy will drop by 10% or even more in more complicated data set of that. And this variation drop mainly comes not from the circuit level, but from the device of the RRAM themselves of that. In addition, some types of non-volatile memory devices also suffer from the temporal variation, such as retention and endurance of that. That's the #1 problem on the robustness of that. The second one is also interesting, is on the scalability. As we talk about, if you cannot design a large array of either SRAM-based or non-volatile memory-based one, for the non-volatile memory or like RRAM, the size is limited by the sneak path and other one. So typically you are staying with maybe 128 by 128 or 256 as a maximum value of the size. To map an entire sort of the AI algorithm on that, you need many of those crossbars or ties of that. So you actually have to build up a network on chip to connect all those things all together. But in this case, if you look at the simulation result of that, depending on which algorithm we're talking about, the interconnect or those wires can take up to 80% or even 90% of the latency and more than 40% of the energy consumption. So basically, essentially, when you propose in-memory computing, you hope this one can solve the memory access problem, as we discussed at the beginning of this talk. But you actually now increase the overhead, not to access DRAM, but to move data around on the same chip around over here. So interconnect in the large-scale memory, in-memory computing is a big issue. Last but not least is the peripheral circuits. In the SRAM-based ones, we have seen that the peripheral circuits takes more than 50% of energy consumption of that one. Similar things are even worse here. The left side is showing the crossbar structure of that with the device in the middle. And this is one, when people present, this is what they usually typically present, because the crossbar seems pretty big in the wall. But if you look at the real silicon design, it's not the case. This is a 90nm test chip for the XNOR RRAM, right? And 1/3, actually 1/4 of the test chip is taken by the RRAM array, including peripheral circuits. And the other are decap, clock generation, and other controls one. But if you zoom into that middle part of the 1/4 of the entire test chip, the ADC is actually 6 times larger than RRAM crossbar. And again, those controllers and decoders and mux are also 60 times larger than RRAM itself. So actually the RRAM, which is a key part of innovation, only takes a tiny portion of the one inside. The rest are all peripheral circuits. And then if you see a silicon data like that, you will question yourself, why I'm going this way? Why just I don't do a digital Mac, right? And I spend so many efforts here to make it complicated and do that one. Why I'm doing that? Well, the reason to do such a large ADC is because you want to make sure that the output from the RRAM will not lose the accuracy or will not lose the precision you need, especially when you use multi-level of RRAM here. But that's a price you have to pay. So in quick summary, if we cannot solve the scalability issues and also those peripheral circuits issues and robustness issues for the RRAM, it will be really hard for RRAM as a practical solution on hardware for AI acceleration. To explore all those things, we propose first the simulation result of that. So we have an end-to-end tool called the SIAM tool to take care of those issues and to evaluate how bad those issues are. I'm going to go over them based on the real data we measured from 65nm wafer of the RRAM device to embed robustness issues inside the simulator. Then I'm going to present you 2 types of the accuracy recovery techniques. One is called pre-mapping, means that before I map to the hardware, we try to use a variation-aware training to emphasize and make the model as stable, as more tolerant to the variations as possible. And the second part is post-mapping, which means after we map the software into a real hardware of the RRAM, how can we manage that? That involves online adaptation and digital assisted analog computing here. And we demonstrate that one on another 65nm test chip. And finally, I'm going to discuss something on future in-memory computing with RRAM and other types using the heterogeneous integration. So to be realistic, we see many papers talking about RRAM and variations, and I want to really see how much variations we're talking about here. For that purpose, we collaborate with SUNY Albany in US to connect the data from the 1T1R test chip at the wafer level of that. Their device is a traditional hafnium oxide RRAM device of that. The left figure showing the wafer level variation map for the low resistance state. The right side is showing the wafer level variation map for the high resistance state of that. As we expect, the higher resistance it is, the more variation it suffers from that. And the lower resistance part actually has a better variation map we have here. And if you look at these ones here, the left plot showing just replot the device properties connected from the wafer for the off-on ratio, and at each ratio here, how much variation we talk about here. If variation is too big, then we cannot use it, right? We prefer the variation as small as possible. So practically, we just limit our usage of this one to the left bottom corner of that, with off-on ratio at about 64. This is already better than the FerroFetch or MTG and other types. So that's why people are doing more research on the RRAM itself. The variation is about 5% as a sigma value of that. And for this specific device, different from some other types of the RRAM device, the temporal variation is not a major issue, as the right plot showing here. The resistance does not really fluctuate too much through the time when you do multiple cycles of that, so which means they are relatively stable over there. So the static right variation is a key issue that hurts the robustness of the SRAM-based in-memory computing in this device technology itself. And in our ones, we embed those real data into our simulator of the SIAM, and SIAM is open source one. You can access it at the GitHub link I posted over there. We also add circuits and architecture flavors and components into it. For the circuits, we are using the Flash ADC, and we design ourselves at different technologies, including 32 and below. And we also calibrate our model with the other people's published data for the ADC and other costs of that. Last but not least is on-chip interconnection. And we know that each crossbar won't be too big. And for in-memory computing, we prefer to pre-store all the weights or all the models on the same chip, because then we can minimize the memory access between the DRAM and your computing chip, right? For that purpose, we need a large number of tiles to map all the weights from the AI algorithm on the in-memory computing chip here. And then we need a network on chip to manage that. Network on chip, or the network itself, right, could have different topologies of that. You could start from as simple as H tree structure, become the point-to-point network, or it's MOC, but on top of the simple tree structure, you have a router of that, or you can have a full mesh to connect data from any point to any point. They have different trade-offs from left to right, and from left to right, the communication and the metal resource cost will go higher and higher from the point to point all the way to mesh. But also the mesh has the most flexibility and the largest bandwidth of that. We embed all those different topologies into our simulation tool to support different algorithm needs. Some small algorithms, if they're not too many tiles, you probably just need the point to point. If you have a really large algorithm and need many, many tiles, then the full mesh might be the choice you need to choose. So this one is one we summarize of this tool, and this one has been used to do different kinds of studies. We can take the algorithm you specify in the PyTorch mode of that, and take the technology specifications like RRAM, SRAM, or other types of memory into the consideration. And the right side, we define the circuit topologies, circuit models of that. And by doing the simulation, we can estimate if you run these algorithms with a realistic, for example, RRAM device at maybe 3 bits, what's the accuracy you're going to see eventually? And on the variations, how much depolation that will be? And also, what's the total energy consumption from each component, including both the computing part of in-memory computing, but also the peripheral circuits that cannot be ignored in such a scenario of that. And then we also include other performance metrics, such as latency, area, to do a realistic estimation of that. So I'm going to choose some interesting results, and this one has been used to drive several test chip design for the in-memory computing and also some in-sensor computing projects we have been used of that. So when you run the simulation, the first thing that we notice is that in the mathematical day, we prefer the RRAM or the non-volatile memory has as many levels as possible, because mathematically, the more levels you have, the more precision you can represent the data, and the better accuracy will be. On the other side, as we talk about the realistic device, right, the off-on ratio is limited. If the total amount, the range of the data is limited, then the more levels you split them out, the more sensitive you're going to be under variations inside it. Indeed, for this ones, as you can see from the left figure, the more levels you split from two levels, which is binary, toward n levels or 16 levels, which means 3-bit or 4-bit, the more levels you cut them out, and the more variations you're going to have, the more accuracy loss you're going to experience. So this is really bad, because that's against the original motivation to use RRAM as a multiple bit in memory computing. And if the multiple bit means more accuracy loss, nobody is going to take that one inside it. And to the right side, we also show that in this case, if we want to keep the accuracy the same from the crossbar, the ADC will be a big component. Sometimes you need 5-bit ADC. And if you want to use high level of the RRAM with a large array, your ADC will go from 5-bit to 8-bit. That totally dominates the accuracy, the energy consumption and latency in such a design. So those are the challenges we have. And how people solve that? Well, people are aware of those problems. We have to solve that. The solution usually comes from 2 steps. One is called pre-mapping, which means before we implement the algorithm on the hardware, we initially refine the tuning process of that. So in the training procedure, we embed the statistical device variations with mean and sigma into that, and using some methods such as knowledge destination and other ones to train the algorithm again to make the algorithm more tolerant to the variations itself. And this one can help bridge the gap between the ideal model and the realistic model of that one, because it is sensitive to the variation now, but it cannot fully recover the accuracy because you do not have a precise knowledge at this point of the exact hardware point, how much variation it is. That's a more device issue over here, right? You can only know the statistics of that, the mean and sigma of that. So it cannot fully recover the accuracy. One point I want to propose, which is different from other people's variation training, is actually the model stability issue inside it. For AI algorithms, essentially the training procedure will search a local minimum that can give you good accuracy. And in that sense, we are able to plot out this one called the loss function, the control of that, as you can see from these figures. We can evaluate how stable you converge to a local minimum of that. And depending on the algorithm of choice, you may have a more rough model or you have a smooth model of that. This is, for example, here, I give you 2 examples for the landscape of the loss function. And one is from ResNet, one from DenseNet, 2 algorithms for the same data set. They achieve a similar accuracy. But if you look at the entire landscape around the local minimum after the training, the ResNet is rougher than the DenseNet. DenseNet is actually quite smooth over here. What does that mean? That if it is smooth, they actually have a hope to be more tolerant to process variations inside once you map them out. So that's why we think, hey, model stability could be an additional new metric when you do the variation aware training to amplify the robustness of the algorithm itself. Indeed, if you look at that one here, there seems a correlation between the accuracy also of the local minimum and the roughness of that. And if we see that one for the same sort of a CFAR10 data set for ResNet, DenseNet, and VGG, the less rough it is around the local minimum, the better accuracy it has over there. So that's why DenseNet is better than ResNet, and ResNet is better than VGG and other types of that. So we like this idea, and we embed the model stability or the landscape of that one as an additional metric in the variation aware training, and we start training that one in it. And we also observe that when you inject the variations through the training procedure, you're actually doing 2 things at the same time. One thing is positive, means that you're trying to expose the variation to the training procedure and persuade the algorithm or the training to be more stable or more tolerant to that one. The landscape used to be sort of a smooth of that. On the other side, it's also causing some negative impact, because when you inject the variations round by round in your training, you disturb the training procedure and make the training less stable than before. So the good choice is in the middle. So you need to choose an appropriate level of variations to train the algorithm and to find out what's the most stable solution in terms of roughness and landscape of the training. And these variations, or the inject, when you do the training, the amount of variation is different from the real device variations, because the stability of the model is an intrinsic property of the model structure, not by the device itself. So usually the optimal amount is different from the device variation you have. So as this example is showing here, by choosing an appropriate level of variations in the training, we are able to achieve up to 19% of the improvement of the model accuracy by choosing the most stable model as a choice of that. But as we said, only the variation array training during the pre-map one will not be able to fully recover the accuracy. We still hope we can have some way to manage variations after we have the silicon hardware in front of us. That involves something called post-mapping here. And here, the idea we look at back is that we look at the implementation of the hardware, right? RRAM can have multiple levels, but it has a sensitivity to variations here. SRAM, on the other side, has a complementary property. SRAM is larger, but it is more precise and more stable than that. In addition, you don't want to write too many times into RRAM, because the write procedure of RRAM is really expensive. You just need to do one-time deal of that. So by doing that one, we propose such a hybrid idea to have one RRAM array in conjunction with the SRAM array of that. And as the left plot showing here, what we are doing here is that we map the model after the variation array training to the RRAM. And then we activate both RRAM and SRAM together. We send the data into it and use the software to monitor the accuracy loss of that. If there's accuracy loss, we use the training algorithm to generate the gradients. But now the training only happens, or the back propagation only goes through the SRAM. We do not want to write RRAM again, because every write into RRAM will trigger more variations into it and more instability into it. So now the training only happens to SRAM. Then after training SRAM one time, we input more data, going the forward again, step by step, follow the training procedure automatically to train the SRAM to compensate the RRAM variation at the final output of that. In this case, we do not have to adjust RRAM value to the original training value. We actually initialize new training on SRAM to make sure the entire model, or the ensemble model, in combination of both RRAM and SRAM together, will provide the baseline accuracy to fully recover it. So as the simulation result showing here, indeed, we are able to pull back the accuracy. As compared to traditional read, verify, and write procedure, we are much, much faster and automatic of that. There's no human intervention here. Everything is done in software and hardware all together of that. And this additional one is really effective through the online adaptation and training to use the SRAM to compensate the accuracy. Inspired by such a new scheme, we are actually develop a test chip to want to demonstrate this hardware works really, really well. So this is the one we developed last year, also in collaboration with SUNY, to develop the test chip of 65 nanometer, including both RRAM and SRAM together. The architecture looks here, and on the left side, it includes a 64 by 64 analog in-memory computing using the 3-bit RRAM array inside. On the right side, it also has a 32 by 64 digital SRAM MAC operation of that. And this is the one to make sure that this SRAM will be activated together with the RRAM to merge the output together. The output between the RRAM and SRAM can be also shifted by 0 to 2-bit, because the argument is that RRAM will still be the main model. If there's any variations here, it will be a fine-tuning of the output. So SRAM does not need to be at the same significance as the RRAM output. It can be shifted toward the right side by 0 to 2-bit of that. We are still testing this chip. We just received a couple of weeks ago. So I hope next time I can present some real silicon data to you. I want to show you some post-layout simulation results. And in this case, we can see that with the SRAM compensation, or with the digital assisted analog in-memory computing, the accuracy is pulled back. And actually now, with a higher bit inside RRAM, the recovery becomes easier, because the more precision of RRAM still provides you more larger space of mathematical representation of the data itself. And furthermore, we can run the pruning of the SRAM to reduce the overhead of how many bits of the SRAM we need. And again, higher RRAM precision helps to do the pruning and saves the number of bits or the overhead from the SRAM side of it. From simulation, in most of the cases, the SRAM overhead, including both the SRAM array, the readout circuits, and the digital MAC of the SRAM part, is less than 5% in area and less than 0.5% in the power consumption when we do the inference. And that is really attractive to people to use this method as a good hardware platform, reach the high accuracy, but also minimum overhead. The only exception here is the mobile net, because the mobile net is such a compact model. It takes about 20% extra overhead if you try to compensate the variation. It's much more sensitive and does not have too many space to tolerate the variations. But even that is just 20% of that one. It's still acceptable for people. And for the future ones, and we have demonstrated that one so far, the SRAM-based in-memory computing, the RRAM-based in-memory computing, right? And we also know that in the future, we need to solve all the scalability and interconnection issues. Indeed, with the algorithm become more and more complicated, if we really want to use in-memory computing and to map the entire model on the same chip, it will be amazing to see that left portion here, the chip will be quite big. Indeed, for many algorithms, even just a small DenseNet or VGG19, right, the chip area will be exceeding 800 millimeters square. That's the maximum monolithic chip we can fabricate, limited by the fabrication cost, the yield issues, and other issues inside. So for that, a single chip will not be able to accommodate and support AI computing of the entire machine learning algorithm. So the solution down the road, we actually need to have more innovative ones. And one of the promising solutions is heterogeneous integration. Basically, we rely on 2.5D or even 3D advanced packaging to integrate multiple chiplets all together. Those chiplets can be FPGA, can be CPU, and can be in-memory computing as a co-processor to accelerate AI algorithms together. And for this reason, we expand our SIAM tool to support all those simulations here. We already released a model of the NLP, like AI, such as the interconnection part of the silicon bridge, as well as the driver, such as AIB released by Intel, and to support the 2.5D integration. We also include the different types of DRAM engines like DDR3, DDR4, and HBM altogether. And right now, just this month, we are finishing our 3D integration to support TSV and other simulations inside our simulator. Down the road, more and more simulations, you're going to see that it's not only the computing, but also the communication. Data movement will be a key issue in large-scale AI computing. And this DNA simulation with the SIAM actually already gives some really interesting ones if you want to expand from a traditional monolithic chip into a chiplet system over here. And as the simulation showing here, right? If you use the traditional 2.5D ones, the NOP instead of NOC will be heavy cost, because when we try to move data from one chiplet to another chiplet, it is still more expensive than on-chip interconnect of that. So these are some issues we need to be really careful. And in addition, at the bottom one showing here, we also propose something called big little chiplet to support AI computing, because AI algorithms are not uniform at all. At the beginning layers of the AI algorithms, there are usually more data generated, but fewer weights are needed of that. And toward the end of the classification and other algorithms, you usually need much more weights to finish the fully connected layer and other MLP type of operations in both the transformer type and the CNN type of that. But you don't generate too much output data. Final result could be just a single bit of this is a phase or not phase, right? So for these ones, if we want to do in-memory computing, for the beginning layers, we prefer a little chiplet that does not need to store too many weights, but need a large amount of bandwidth to support a large amount of data communication. Toward the end, final layers of the AI algorithms, we prefer big chiplets that can pre-store lots of weights inside, but bandwidth does not need to be too much because the output data volume is small over here. And by doing such a big little chiplets, our simulation using SIAM showing that one, this can achieve more than 300x reduction in the energy delay area product of that. So based on these tools, those are just some early results. We hope we can collaborate all together with everybody, and I encourage you to use this tool. Maybe this one can help your research too in the in-memory computing domain of that. So in summary, in this talk, we talk about the bottleneck of the in-memory computing. As in-memory computing is a promising technology to drive the energy efficiency for future AI acceleration, but we also need to be careful about the robustness issues from the device, from the circuits and other components. We also need to be careful about the peripheral circuits, especially the ADC cost in the middle of that. And finally, we need to be careful about interconnection, the network to connect data movement all together. As the scale goes up and goes larger and larger, the interconnection becomes more and more dominant of that. The research in these domains involves the joint efforts from the algorithm side to make the algorithm low precision as much as possible. Indeed, for the SRAM-based in-memory computing, we prefer a binary net, just a single bit of the weight, instead of higher precision of that. And we also need to be aware of the different solutions to improve the robustness and scalability before or after mapping of that. And finally, I do believe the heterogeneous integration will be the future to go to integrate the different types of technologies from the device to the interconnect to the system altogether to drive this field. By saying that, I conclude my talk today, and I would like to acknowledge all our students working together on this project and funding agencies that support our research until this point. Now, thank you very much for your attention. I'm open to questions.
Thank you, Professor, for this very interesting talk. If you have any question, feel free to ask it in the chat. I have one question personally. One little bit more, but SIAM is allows to train. If I understood well, SIAM allows to train neural net. AI, taking in account some hardware specification, some hardware perturbation. Would it be possible to add it to predict some consumption linked to online on-chip training with this kind of software simulation tools, or not? As on-chip training is important way, important field of research in current articles, into current research. So, what do you think about it?
Yeah, so current SIAM tool is mainly on the inference stage of that. So basically, give input what predict the output, right? And the training or online training can be supported with external package. Right now, for example, we write a Python wrap around it to finish online training of that. So the online training is not embedded into it itself.
Okay. Would it be would you think it would be possible to
embed online training?
Okay.
Yeah, it's definitely possible. We are actually right now we're developing a new simulation tool called SIAM to support the heterogeneous integration with different types of chiplets, and we also want to expand from in-memory computing toward different types of computing platform like CPU and other types. And then in that one, we're going to build it based on the PyTorch, right? And we're going to support both the training and inference together.
Okay. We have one question from Antoine Gauthier. I will put you here. Up. Okay, yeah. We have one question from Antoine Gauthier.
If memory is analog in spirit, is in-memory computing is essentially analog in spirit? Is it a consequent disadvantage considering industry constraints like IC design cost, impulse time and memory scaling difficulty, etc.? Yes and no. Interesting question. So I think you are correct that if we talk about analog in-memory computing, it is not an easy path to transfer this one to industry, because in an industry practical environment, digital is much more welcome to be more robust on the noise and other issues. That's why in recent years, if you look at the industry papers from TSMC and others, they all use digital in memory computing. They basically don't break into the memory one. They just reduce the size of the memory bank and additional adder tree outside to do that one. We also have a test chip on that, and we're going to submit a paper right away for the in-sensor computing. In-memory computing for analog is actually really interesting, but also really challenging. Analog in-memory computing is a really good topic for academic research still at this point. It's not ready to be transferred into the industry yet. There's still several main issues we have to solve, including the robustness of the tile itself. And also, can we get rid of the ADC, and can we get rid of other digital components to finish an end-to-end analog computing in the environment? The later we can convert it back and forth between analog and digital, the better for analog in memory computing. So still lots of research need to be done to make analog in-memory computing as a practical technique for industry to adopt.
Okay, so there is a second question from Antoine Gauthier.
Yes. So second question is, AI, as you mentioned, is a promising and already well-covered area for in-memory computing, especially for embedded and AGI. But is there other trends? There are many other trends actually going on. The one branch I talked about is to scale the system from a monolithic chip into 3D. When you have really 3D, how to really map and compile an AI algorithm to a 3D system is really a good topic to look into. And there are also other topics, can we also expand our AI and in-memory computing into other application domains? For example, in-sensor computing, right? We are not talking only about computing here, but in reality, a full dynamic system includes or starts from the sensor front end to the computing side, and then finally to the conclusion and prediction of that. Can we include all these things into one design environment to do that? And third one is that for the different types of computing techniques, in-memory computing may not be the only one, because in-memory computing, as you can imagine, is really good at to solve dense computing problems, because now the entire array will be activated on and off at the same time. If the computing itself is dense, like the convolution, it's really good to use AI in-memory computing. But for many other AI algorithms, such as graph learning and other ones, they are not dense at all. They're sparse. So how can we combine the dense in-memory computing with other hardware accelerators to handle the sparse data and adapt between different types of algorithms can be also a good trend and good research topic for you to consider.
Okay, is there any question in the chat? I don't see ones. Okay, I think it's also time, so thank you, Professor, for being there today for you. And thank you for this very interesting talk. Thank you for people that were here today. And don't forget to follow us on LinkedIn to be aware of our future event. And see you next time. Thank you.
Thank you very much. Final question here. There's one. Is it possible to replace a flash ADC with no power ADC architectures, for example, a SAR ADC to save power? Yes, I think there are active research going on already on that topic. So how to improve the ADC efficiency? Yes, and people are doing the SAR. I know that one. Yes. So you can look into that one too. Yep. Or eventually maybe even get rid of the ADC.
Okay, is there any question? Again? Okay.
Thank you very much for everybody.
Yeah, thank you thank you again.
Thanks, Matthew.
And thank you, Professor, for your very interesting talk. And this time I think it's a good one.
Yeah.
Okay, so see you next time, and don't forget to follow us on LinkedIn.
Thanks, everyone. Have a good night.
See you.
Bye.